The same problem of summing up from 1 to 10 is actually done by what would appear to be magic, by simply going sum 1, 10, done. It's not quite as easy as that. One of the questions that I get asked when I introduce myself as a computer scientist is what exactly it is that I do, and the easiest answer for that is programming. There are different styles, and a lot of people might not be aware of them, so today I'm just going to contrast two of the most popular ones, namely imperative programming and functional programming, adding the numbers from 1 to 10 in two languages, Java and Haskell. So we'll start with Java. We begin by introducing a variable total, an integer, and saying, well, that's 0 to start with, because we haven't added anything up yet, and that's comparatively easy. And the actual meat of the loop is just done by opening up a for loop, where we say for some number int I equals 0, and I less than or equal to 10, then I plus plus. And what that means here is we've got this little tracking variable I, which we initialize to 0. We're going to be repeating this loop as long as it's less than or equal to 10. And every time we repeat the loop, we're going to increase I by 1. We're adding numbers 1 to 10, so the obvious thing to do is to say, we'll change the variable total to the result of total plus I. What we have here is we've got an appearance of the equal sign. Some people would look at this and go, right, this is clearly the mathematical definition of equals, which means the left hand is equal to the right hand side. That's not the case in Java and other C-like languages. What this single equals actually means is an assignment. We're saying that total is now equal to the previous value of total, and we've edited it in some way. In this way, we've added 1 to it. If we were to have a double equals, then we would be checking for equality, in which case this total equals total plus I would be false in all cases except for when I was 0. So this kind of statement that involves variables such as total is characteristic of imperative languages where the main method of computation is assignment of values to variables. It's going to say we start with total is 0, and we say if I is 0, total equals 0 plus 0 is 0. Then we go back, we increase I by 1, so now we say okay, total is 0 plus 1, which is 1. We go back, I is now 2, total is 1 plus 2, it's now 3, and we repeat. Once we get to the end, then we're done. If we want to call total, then it would just be the result of going 1 plus 2 plus 3 plus da 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 da, and eventually at the end of it we'll have total, if we were to do a call on it, is 55, because that's the sum from 1 to 10. This is a characteristic of imperative programming in that we're referring to variables that are defined globally. This is a simple example of adding a couple of numbers up in an imperative language. Namely, this is done in Java. What I'd like to do now, having just spoken about the mathematical definition of equals, move on to another language in which to do this summing from 1 to 10, namely Haskell, which is a functional programming language. So the same problem of summing up from 1 to 10 is actually done by what would appear to be magic, by simply going sum 1, 10, done. It's not quite as easy as that. There is a library function in the background that's explaining how sum actually works. The first thing that we need to know about the sum function is what its type is. So we would say that the function sum is the function that takes a list of integers, that's a syntax for list, and it returns a single integer. Namely, if we take a list from 1 to 10, we're going to return the sum of them. And what we're going to do now is we're going to define this function in terms of pattern matching. A function can have multiple definitions associated with the value that's given to it. What pattern matching is a way of deciding which definition of a function to apply in a given case depending on the structure of the input. So let's say that we are looking at a function that takes lists, then that function could be looking at an empty list, it could be looking at a list with one element in it, or it could be looking at one with more than that. A simpler example perhaps is a function that's defined over the booleans. So a boolean value can either be true or false, and a function that's defined over that, the obvious one would be not. So not true is false, not false is true. And if we're using pattern matching, I'm going to take my value and say, is it true? If the value that I've got is true, then I use the function definition of going to false. if the value that I've got is false, it'll say, I'll look at this first line, have I got a true? No, I don't. I'll go down to the next one. And then I'll say, okay, well, I've got a match there. When you're looking at a function, your input, you will try and match from the top. Say, is that the one I need? No. Right, look at the next one. Is that the one I need? No. Is the next one? And it may be the case that you don't have all of the patterns necessary to fully define your function, in which case Haskell will give you an error. It'll say non-exhaustive patterns. So if we have this sum of a single number, this is a list of one element, we say that the result of the sum of one number is just that one number. And if we have a list of more than one number, then we would write it like this, sum n n's. This is just shorthand for saying that the element that's at the front of the list we call n. All the other elements are called n's, and we would just define that as n plus sum n's. So this function sum is defined recursively, that is to say it's defined in terms of itself. What I might like to do for some people that aren't familiar with functional programming is go through a very quick example of how the sum function works. Sum of 4, 5, 2. So we can refer to this function here throughout and see how this is equivalent to the Java representation that we've got over here. So what pattern matching involves, we look down and say, are we looking at a single list? No, we're not. So we can move down to the next pattern and we say, okay, in this instance, this 4 is the n, and this 5, 2 is the n's. So this is defined to be 4 plus the sum of 5 and 2. Grand. Next step, we're going to, again, sum is defined in terms of itself. We haven't gotten down to base value yet, so we're going to have to carry on. So we do so by saying, okay.
So what do you mean by base value?
Okay, so functional programming, the main method of computation for that is applying arguments to functions, as compared with Java, where I said it's assigning values to variables. By here, when I say we've reached a value, I mean that we've evaluated a singleton and returned n. So to carry on with this evaluation here, what I want to do is to say, okay, that's sum 5 plus sum of 2, because in this instance here, this was the n and this was the n's. And now I carry on and I say, oh, well, if I'm going to be correct, I'm going to bracket that, and I'm going to say 4 plus 5 plus, and now I can look and say, pattern matching, start from the top, have I got a singleton list? Yes, I do. So what am I going to return? Just that number, 2. So now I can start boiling it down and say, well, that's 4 plus 7 equals 11. So what I've gone through here is just a quick example of how a functional programmer would take the approach to the sum function, defining what the sum actually does, as opposed to looking down and doing it in terms of variables, saying, well, track this and add it to this, and eventually the result will fall out of it. It's probably worth saying, though, that this isn't how sum is defined in the Haskell library. It's actually defined as sum fold L plus 0, but that is dark art that I don't quite want to get into at this video. So one particularly important thing to take away here, given that I've been contrasting these two, is that in this example here, where I've been summing 1 to 10 in Java, this has revolved somewhat around this variable total, which has been evolving as the for loop progresses. I've been updating this total variable and increasing it to reflect a new value until I get to the end of the for loop. So this is characteristic of imperative programming languages, the fact that I have an external global variable that I can update at will, whereas in functional programming, in Haskell, there is no state externally. I'm not calling anything from outside this sum function. This sum from 1 to 10 is defined entirely in terms of itself. There is no reference to a total or something that's not explicitly reachable from inside this function body. And that's because functional programming languages, or purely functional programming languages, don't allow for side effects. And a particular example of a side effect is a mutable state, where by mutable I mean it can mutate, you can update it. So it can change from one value to another as a program progresses. It's worth saying that these are both high-level instances of languages and particularly simple instances of fragments from these high-level languages. These do look quite different in the way that they approach things, but they will be boiled down to machine code, and very similar machine code at that, given that it does something quite simple and in effectively the same way. Summing 1 to 10 is not something that can be done in very complicated ways by different compilers.
What if the universe is just a computer simulation? How would we know? What sort of things might we expect to see? Could we ever tell? Could we ever be able to work out that we're, living in part of a simulation, or we're just
pivot and putting all elements less on it on one side and greater than it on the other side, and then it does that again on each side. So you can see it's done all the left-hand side, and now it will start doing the right-hand side. So there's the pivot, it does all the left-hand side, picks another pivot, keeps doing that until it's sorted.